Hello?
Yeah.
Is it working? Yes. Good afternoon, everyone. My name is Olimpia, and today I want to share with you part of my work on a Slums Generator tool, which I developed as part of a game development pipeline. The original purpose of it was to create massive slums complexes. However, the tool's use of instancing allows for great flexibility and can be applied to various scenarios and settings. To start, let's take a look at how this tool fits in the production pipeline. In Unreal Engine, level designers set up a blockout geometry that serves as the first input for the tool, while artists design one or more sets of slum units that the tool will place and instance within the blockout. As they use the tool for set dressing, they provide feedback and the tool is updated and improved according to their and the game needs. Finally, the output of the tool is baked into an actor or a blueprint. Now let's dive into how the tool works. First of all, to streamline my workflow, I added a switch node that checks for primitives in the input geometry. If none are found, the tool uses test geometry instead. Flat edges are then dissolved from the input blockout to be able to distinguish between solid and plane geometry based on the number of normals. Solid and plane geometry are processed separately. For solid geometry, a VDB rod is used to create a space between the slum units and the collision, which matches the input blockout geometry. Next, some noise is applied to later inform the scattering of the points and make their distribution more organic. A point from volume node creates a point grid inside the volume, then a fuse node snaps the most external points to the surface of the geometry and aligns them with the surface normals. The interior points and the bottom points are deleted, while the remaining ones are clustered. And with clusters, I can give the user control over the size and amount of clusters that can be adjusted. Finally, the normals are flattened on the XZ plane, as you can see from this test geometry of the slum modules, and then a slight noise is added to the point's position for a more natural look. Now to the plane geometry. For each plane, a grid is created and matched to it so that the instancing point can be determined by the grid points that intersect with the plane. Then a noise is applied, the normals are flattened, and finally the points are clustered based on adjustable parameters, just like in the for the solids. After obtaining solids and plane points, each unique instance of the slum units is randomly assigned to the points using the Unreal instance attribute. Then the min and max point position for each piece are used to remap some values to control slum's distribution over the pieces. There's a limit parameter that removes points above a specific height, creating a flat roof for the slums. The fade start parameter fades out points around a certain height, and the variation parameter controls the range of the fading effect around the fade start height. And this results in a more natural looking fall off for the points density, making it appear denser on the bottom. Finally, collisions and back wall are set up. The back wall can be customized by the user, who can apply a material and adjust texel density. The merge components are then configured with a couple default baking options that simplify the user workflow. So creating tools for game development, I learned some key points that are essential for making these tools actually useful. Cooking time is key because we want to make it as short as possible to have several and fast iterations. Runtime performances also are very important, so optimization of the tool output in engine is important for a smooth gaming experience. And for these 2 points, both instancing helps a lot already. And usability is another key point. You want the user to actually test the tool and give you feedback on that, so that you can be able to adjust it to their needs. And for that, it's also important to keep parameters simple. And that was it for me. If you have any questions or would like to connect, please reach out, especially in person and on LinkedIn. I'd like to mention that I'm open to internships starting September, and thank you very much for listening.
All right. Well, hello everyone. My name is Catinca, and I'm a student second year here at BUAS. And I'll be talking about a tool that I developed and I'm still currently working on in Houdini for the procedural generation of levels and room layouts for a top-down action video game. First of all, as a little bit of context for this tool, I would like to show you a bit of gameplay from what my team and I have been working on. And we are in the stages of developing a top-down isometric roguelike in a custom engine. And we're drawing a lot of inspiration from games such as Hades. But instead of making the rooms prefabbed and then randomly putting them in a certain order, we decided to go with a procedural approach and do procedurally generated rooms, which will help our project from multiple points of view. It's going to be the main pillar of our game, and it will aid level design to help with set dressing by working with GLTF files and hierarchies. It's going to allow our team to avoid complications with module placement, as well as to increase replayability and allow us to quickly iterate level variations. As the technical artist of the team, I've been working on creating and improving this room or level generator, which I have mainly based on the design principles that guide Tartarus in Hades. So the rooms are mainly enclosed by walls, but with a lot of open space for the player to constantly be on the move, built around tactical maneuvering around strategically placed props, and it's allowing the player to keep running around in circles in each room to dash and dodge attacks. And as mentioned before, the most important rule that drives this generator is the spacing of the props to allow for the player to run in circles. And you can see on the diagram, that's basically the backbone of the generation. The black point in the middle, which is usually a prop, the red path surrounding the prop area, and the yellow path, which is more like the area that the player always has to have free to run around. And the rooms are generated from the bottom up, so they are built around the props. Each tile gets assigned a color value based on gradients, and they start from the main prop points towards the outwards of the level. And you can see on the right side a level generated and all of the player cycles and all of the circles that the player can make while running in the level. The generation is a multi-stage process. It's divided into 2 main stages. The first one is the pre-generation, and in this stage, the main setup of the room is created, so all of the main cycle points. And after that, from that, it builds on the actual level. It creates the floor layout to allow the player to go around them. And you can do that in one of 2 ways. The first way that can be done is with wave function collapse. So it will place, that's a sample input and that's a sample output, and that is a variant of it. It will place randomly all of those player cycles into the level, then build the floor around them. And the second way of doing it is a more symmetrical way by placing vertical, horizontal, or diagonal lines and props on the ends of the lines and in the center. And those can also be manipulated by the user, pushed along their normals to space out the props in a different way for more variation. And the second stage of the generation contains the post-processing of the main room setup, which takes the layout and converts it into an actual level using algorithm layering to populate the space. The first addition to the original layout is the creation of the lava gaps. And that can also be done in one of 2 ways. The first one is cellular automata, where it randomly picks black points, which are the points for the props, and it says, okay, you're a lava start point now. And after that, using the cellular automata, it floods the area around that point without invading the red path of other props to make sure that the player can still move around. The second method is more manual, and you just use a curve tool or a draw tool to select areas where you want the lava to go. And all of this process basically modifies the level, and it can become quite hard for the player to get from the exits in different places, or the entrances. So after the lava layouts are created, the tiles go through cellular automata again to adjust the door points where, for example, it would be way too close to other things, and the player would have too tight of a space to move around, so it adds extra space. Next up in the layering process, the system runs through a Dijkstra algorithm, creating a Dijkstra map starting from the entrances, which are marked with 0, and then a gradient with every cell, depending on its distance, marked with a different number. And every unreached area is marked with -1. And a big challenge was to actually create recursion in Vex because it's impossible in the actual Vex thing to declare a recursion function. So because of that, I created a for loop with a stop condition and created two extra attributes, one for the points of the tiles and a detail attribute that would be used for the recursion. And thus, using the Dijkstra pathfinding running from all entrance points, I could determine which levels were valid by checking if the exits had valid Dijkstra values, in short, if they were indeed reachable. So if there are lava gaps or props hindering the player's movement that would make the level unwalkable, the level is declared invalid, as in the bottom example, where the white areas are not reached ever. That brings me to my last point, which was the recent addition of wall instancing. To break up the repetition, the environment artist created set pieces or modules of 3 different lengths, 1, 2, and 3 units. And each side of the level is then broken up into walls of those specific lengths, allowing the instancing of different modules along the curves. And to also facilitate player visibility, because of the isometric camera angle, we wanted the walls that were in front to be smaller walls, so they're scaled down, and the walls in the back can have like bigger architecture. On the left, it's the Houdini output. So basically, it's either a color-coded and block-out version, and then you can see it with the props placed. And on the right is the custom engine version and how it looks right now loaded into the engine created by the programmers. And that was it. Thank you very much for listening.
Hello and welcome. My name is Alicia, and I will walk you through some of the steps that I took for making this cobweb tool, which can generate textures from a high poly mesh and output them to Unreal on a low poly mesh. So to give you a short overview of how the tool works, its inputs are an Unreal curve and scene geometry through the world outliner input. Those are being fed to the Houdini system, which on the one hand outputs the high poly cobweb mesh that the user mainly interacts with, but I will mostly be focusing on its other outputs, which are the low poly mesh, the generated texture, and the material instance. So in this video, you can see the tool in use. The cobwebs are automatically adjusting and sticking to the environment based on the geometry that I have selected for it. There are also some user parameters available which influence the output of the tool, such as the string thickness or for example, the texture resolution. Then upon pressing the Save Texture button, the texture is being created and can be viewed by switching to the low poly view. Next up, I would like to talk about some of my approaches that I took for creating this tool. So initially, my idea was to use the Labs Maps Baker in Houdini, which is a great addition to its game toolset. However, with the cobwebs, it gave me some accurate results in terms of shape. But what would often happen is that the strings of the cobwebs would be misaligned on a texture. And as I realized, this is simply a result of how texture baking works, since it captures the high poly geometry according to the low poly space normals, which with such an interconnected piece of geometry is likely to always create a misalignment around areas that have a lot of curvature or depth. So instead, I came up with a different solution, and this is about the result that I get now. There is still some discrepancy in terms of shape, but it did solve the misalignment of the strings on the texture. And how I do this is, instead of generating a texture from the low poly geometry as it is, I actually unfold it according to its flattened UV layout. And I deform the cobweb strings to match that flattened UV layout. This works by assigning each point of the cobweb string geometry to the primitive that is closest to it on the low poly geometry, so that they can follow the low poly geometry to its new position once it's unfolded. This unfolded geometry is then projected onto a height field, and the data is being read out by a SOP import node inside of a compositing network, which produces an accurate image representation of the cobweb strings. Doing it this way also gives me the freedom to add and layer some noise to make the cobwebs look a bit less clean and more organic. And the texture can then be directly applied to the low poly mesh, since it's created based on its UV layout. But in order to apply it actually in Unreal Engine, I need to save the output of the cob network first. So as I've shown before, the texture is being saved by user input on pressing a button. And that button actually triggers a Python script that the Houdini asset carries. And it saves the output of the cob network to the disk. It also automatically increments the file so that the user only needs to input a texture name prefix. And this was also to prevent from different Houdini assets in the scene to override each other's outputs. In addition, the script also forwards the path of the newly generated texture to the Houdini asset, which is necessary for applying it to the geometry in the next step. And as you can see in the video, once I change the curve and I save another texture and switch to the low poly view, it will always apply the latest generated texture to the mesh. So in order to use the textures that are generated by the Houdini digital asset, it is actually necessary to go through a Houdini shader first. So the textures that are created are first assigned in Houdini to a principal shader, to the low poly mesh, and then this allows for creating Unreal material attributes that can read out that assigned texture. And in this case, I'm creating a material instance from a chosen pre-existing material in Unreal, and I'm assigning the opacity texture to the corresponding material parameter. And that is in a nutshell how I create these cobwebs from the high poly to the low poly and with the generated texture. Lastly, I would just like to thank Ian Smith and Tim J. Design, which I mostly based the system for the actual cobweb strings on, and my teacher Pedro Santos, who provided me with a base for the Python script that I'm using. If you have any questions, feel free to reach out, and thank you for listening. Next up is Maze.
Hello, everyone. It's a real pleasure to be here today. My name is Matthias Pressler, but colleagues and friends call me Maze, so feel free to do so as well. Today I want to share with you my latest project, combining Houdini and Unreal to create modular sci-fi buildings. The purpose of this tool is to enable faster and more efficient sci-fi world building while adhering to the real-time performance constraints of game engines. With this tool, designers and artists can easily create and modify complex building structures, saving time and resources in the creative and production process. First, I want to give you a brief overview of the shape generation and the balcony options. To create our modular sci-fi buildings, we start by defining the height and the size of the basic shape, which can be either a pre-made custom shape created from a spline input or just a normal curve. Next, we add additional shapes along the height of the geometry using spaced interval placement controlled by a curve, allowing us to create a gradually inwards placement from the bottom to the top, or whatever style we seek, and multiple seats on each axis can be tweaked for the end result. Moving on to the balcony levels, we can add up to 2 insets on these levels to create interesting overhangs and terracing effects. And we can also connect a second tower with bridges. The positioning of those bridges are controlled by a curve parameter, again, based on the building height. And the bridge profile can also be manipulated with a curve parameter. Finally, we add balcony geometry by extruding the balconies outwards. Again, a curve parameter can manipulate the extrusion amount. Here I reduce the amount on the top of the building. And a second part of balconies can be added where needed and shaped in the same way with the curve parameter going from the bottom to the top. To further define the big shape, we can add panels and an exoskeleton. We have the ability to select the panel areas based on a ratio and seat. The panels themselves can be sliced in different ways, horizontally, vertically, or with a fake Manhattan algorithm to create the unique sci-fi angles we desire. We also have the options to add depth to the extrusion, randomize the position with a defined range. Additionally, panels can have insets, beveled corners, and greebles along the sides of the panels to add even more details. And again, seats can be used to tweak it more. The exoskeleton feature is designed to break up the larger shape even more and give more complexity and control over the final appearance of the building. With its shape-aware capabilities and wide range of customization with Voronoi, fracture, and everything, we can have intricate and unique designs for each buildings. Now we have defined the big and medium shapes. Moving on to implement modular assets. To approach modularity, a wide variety of unique layouts, I utilize the shape grammar concepts to place pre-built modular assets. The vertical shape grammar defines the placement of the floors and influences the overall shape of the building, while the horizontal shape grammar describes the layout per floor level, including the placements of corners, walls, and windows. A small example in action. At the bottom, we have some floors describing the entrance levels. Then comes a repeating apartment floors, And now I add some more technical floors in between and on the top of the building. And then we place the highly detailed modular assets and rendered here with Karma inside Houdini. Now a final look at the pipeline with the outputs for Unreal. The shape generator can be merged with the shape blockouts from Unreal. Additionally, the tool can add support structures and overhangs, and also pillars and ivy on the support structures. These and the floor modular assets are exported via point cloud with attributes and materials. And all the other exported geometry got UVs and the possibility to use vertex color noise for the materials. So here's let's everything combine in Unreal. Here we see how the horizontal shape grammar automatically assigns the most suitable patterns to the available space. This is possible to the ability to define multiple horizontal patterns for a single floor layout, allowing for maximum flexibility and customization. By mixing the shape generator with blockouts from Unreal, we can add even more complex shapes and customize it more in Engine. The tool adds the pillars and the structural supports on the balcony levels, while the ivy can be scattered and customized more with parameters, providing the opportunity to add natural and organic details to the building. And finally, we can also enable a ledge per floor level with a bit of customization options. And finally, by simply swapping out the floor grammar, we can easily exchange the modular pieces for a completely different look. I want to I express my gratitude for the incredible Houdini and Unreal community. Without them, this project would not be possible. Continue with the inspiration and support. It's really amazing. Please feel free to reach out to me on LinkedIn or ArtStation. And if you have any further question, let's have a chat later. Thank you.
Welcome to our presentation. We are Olimpia and May, and today we'll be showcasing our toolkit in Houdini for transferring audio-to-face geometry animation to joint animation. So we all know that facial animation is very valuable, but the animation and the rig needed to create it take a very long time to produce. And NVIDIA audio-to-face from NVIDIA Omniverse offers a solution to this by generating facial animation using only a face mesh and audio clips through a machine learning network. The problem with this facial animation data is that it is unoptimized and it cannot be cleaned because the animation is stored on the geometry and not on a facial rig. So we set out to make audio-to-face more viable for game projects by creating a toolkit to transfer its output to joint-based animation, which is more suitable for real-time use. Additionally, we created a system to procedurally rig and skin the face mesh for the likely event that facial rigging is not in the scope of the team or the project. And lastly, the joint animated head can be directly attached to a pre-animated body, merging the two animated rigs seamlessly. All in all, for animators who are the intended end users of this toolkit, the process will be very similar to mocap cleanup, meaning that the learning curve will be minimal for those comfortable with that pipeline. Then for an overview of the features of our system, after audio-to-face has generated the audio-to-face mesh, our toolkit comes into play. The first step is generating a face rig, which can be done in one of two ways. Either automatically, as you can see on the left, where the bones get placed based on the animation, or manually, as you can see on the right, where the bones are placed by the user. The skinning is fully procedural with both methods. The way animation transfer from audio to face onto the rig works is that for each bone, for each frame, it looks at the position of each bound point on the audio to face output mesh, and then offsets the bone to the average of those locations. The skinning weights are also considered for this. This takes about 10 seconds to cook for 150 bones across 300 frames, and then plays back at more than 30 FPS with the help of motion clip.
Now, once you have your animated head, you probably want to reattach it to a body. This is where the head-to-body transfer part of our system comes into play. The system takes in the newly created head animation and its rig, as well as a body that can also be rigged and animated, and attaches them together using input names for important joints. The system uses all the information it gets to correctly align the head to the body, transfer the animation, and parent the joints. The result is a rig that is complete one piece that you can export for cleanup or use in Engine. This toolkit is meant for animators who will likely not be familiar with audio-to-face or Houdini. So when we made our documentation, we made sure to not only describe our tool and how to use it, but also how to set up your mesh for audio to face, how to get the most of the audio to face, what the most important settings are and such, as well as a guide for optimal joint placement in case the user decides to create their own rig using the custom rig method. This was quite a project, so we learned a lot from it. Our main takeaways are as follows. Rigging is complicated, so we found out, especially when you're using matrix attributes such as X-forms and transforms. A lot of things can go wrong. Also, when you're transferring data between softwares or within softwares, we have a lot of instances where FBX files or USD files that we were using did not import correctly or export correctly or were somehow corrupted. This was quite surprising to us. And lastly, our most important takeaway is that clean and varied test data is vital. A lot of the issues that we found during development were not actually caused by our system, but rather by the stuff that we were using, bad rigs and animations. So having a clean and varied test data set that you know works is very important if you want to do smooth development. Then this is the raw output of our system. The following animations of both a stylized and a realistic character were made in less than 30 minutes.
The brethren will still be looking here to us, to the Black Pearl to lead. And what will they see? Frightened bilge rats aboard a derelict ship? No. No, they will see free men and freedom! And what the enemy will see is the flash of our cannons. They will hear the ring of our swords, and they will know what we can do! By the sweat of our brows, and the strength of our backs, and the courage of our hearts.
Now, before we end it off, I'd like to give a special thanks to David Rhodes for setting up the base skinning and animation transfer systems. Without him, this project would not have existed. Here are our socials if you want to see more of us in our work. And nice to mention, I think, is that both of us are open for internships starting in September. Thank you.